always, you can use this. Quizzes are open up. Tests are not. Tests, you are on your own with a calculator, pencil, straight edge, or graphing, whatever, but nothing that connects to the internet. You may not call Regis Philbin. Well, technically, you need a seance because he's dead. You cannot contact Regis Philbin for help with Who Wants to Be a Millionaire. Then again, you probably weren't even born yet when he was hosting it the first time. Probably don't even know who Regis Philbin was.
The main guy who always hosted it or somebody else?
He was the guy that always hosted it. He was the guy who did that morning show with Regis and Kathy Lee, and then what's her face took over, and now it's her show. Kelly? Yeah. So, one question. You tell me what you want to see. It is in your hands. And over there, I've written down, we have already done 33, 39, 43, 46, 57, 57, 59, 60, 61, and 62. Those are the ones we've already done. $34. 34? 34. Okay, so quiz today, I'm going to give you a function as if I was doing, if I wrote down number 34, it says d of r is equal to 4/3 pi r to the third. That is the formula for the volume of a sphere, if you didn't recognize it. Volume of the sphere is 4/3 times pi times the radius of the sphere cubed. And I just took off what comes from actually. The doctor said I should walk around. We are substituting. We are tuning. So your quiz today is going to look like this. And it's going to be question number 1, and then it's going to say, right below it, number 1A or 34A, we want what is D of 3, okay, and then 1B below that, and then 1C below that. We have room to work the problem underneath. Now, underneath that 34A, it's going to say D of 3 is equal to what? Put your final answer here so I can find it. If I give you a place to write your final answer, always put your final answer in that place. Just makes it easier to grade instead of just floating somewhere. You have 5 different versions of some kind of answer, but which one is actual D of 3? So that's why I put it like filling out filling in a bubble on a sandstone. So 34, D of 3, B is D of 3 over 2. And C is D of 2R.
So you said it's going to be a problem like this and a problem like the one we're trying to make, right?
Just a minute.
Okay, so.
There we go. So this is just substitution. So if I replace this R with a 3, I got to replace that R with a 3. So B of 3 is equal to 4/3 times pi This is now a 3, so that's going to be times 3 to the third power. Now, parentheses are good habits. Using parentheses is always going to make better habits. Doesn't matter if I'm just plugging in a 3. I could get away without using a parentheses around a 3. But if I use parentheses all the time, I'm going to be better all the time. So b of 3 is equal to 4 over 3 pi 3 to the third is 27. So times 27. No decimals, just simplify the final answer. So you could multiply 4 times 27, but then make sure you reduce if it does. Right here, 3 goes into 27 9 times. So 4 times pi times 9 is 36 pi. That 3 reduced, so in the denominator you have 1. 36 pi over 1 is just 36 times pi. Okay. I could have also gone, hey, that's 3 to the first, that's 3 to the third. So 3 to the first goes into 3 to the third, leaving 3 to the second. Do that too. As long as I see the work. I mean, I'm letting you use calculators, but I'm hoping you don't have to use a calculator. Okay. Here's where parentheses really makes a big deal. Plugging in 3 over 2 now. That means over here, replacing r with a fraction, 3 over 2. So 4 thirds times pi. That doesn't change. But now the radius is 3 over 2. 3 over 2. And you've got to put it in parentheses to raise it to the third power. If I just go 3 over 2 without a parentheses and raise it to the third, the only thing being raised to the third power is the 3. If you write it like that. If you want to raise the whole 3 over 2 to the third power, the 3 over 2's got to be in parentheses. So this is b of 3 over 2. Perfectly fine with you going to this next step. 4 thirds pi 3 over 2 to the third power is 27 over an 8. Ask if you need to. I promise I'll never say, you should know this by now. I'm not going to say that. I'm marked the wrong class. No wonder I can't see something. Yeah, right. All right.
So did you get it by, so it's like 3 times 3 is 9, 9 times 3 is 27.
Yeah, so 3 over 2 to the third is 3 over 2 times 3 over 2 times 3 over 2. So 3 times 3 is 9, and then times the 3 again is the 27. 2 times 2 is 4. 4 times 2, there's my 8. But one of the basic properties of exponents, if you have a fraction to an exponent, a over b to the m power. If you have a fraction to a power, you can just raise the numerator to the power and divide by the denominator to the power. Each one, numerator and denominator, are both raised to that same power that's outside of the parentheses. So right here, you could just go, this is 3 to the third over 2 to the third. 3 third, 27, 2 to the third, 8. Okay. Simplify again. Well, 4 does not reduce with 3, but over here, this denominator, 4 and 8 have a 4 in common. You can reduce a 4. 4 goes into 4 once, 4 goes into 8, leaving a 2. 3 doesn't go to 1, but 3 does go into 27 like we did over here. This 3 can go to that 27, leaving a 9. So across the top, you have a 1 times pi. Remember, this is pi over 1. 1 times pi times 9. So that's 9 pi over, this is 1 times 2. So over 2. So if the radius of the sphere was 3 over 2 feet or 1.5 feet, it would be 9 pi over 2 cubic feet in volume. Okay. Any clarification there? And I'm setting up your question just like you're seeing the homework problem. Going to give you a number to plug in, going to give you another number to plug in, and now you got to plug in something with a variable in it. So now we're going to plug in 2r for that 1r. So I'm going to replace that 1r, and it's going to be replaced with a 2r instead. That means this r is going to get replaced with a 2r instead. As a whole, that whole 1r is now just going to be rewritten as a 2r. So v of 2r is 4/3 times pi, and it was r to the third. Well, this is what I'm plugging in. So it's 2r, and I raise that to the third. Whatever I replace the r with here, or whatever variable it might be, whatever I put in here, I put everywhere else I might have that r. Or whatever it is, an x or whatever, t. So now we simplify. So v of 2r is 4 over 3 pi. When you have a product to a power, this is for fraction. If I have a times b to the m, then you just raise each factor to the m. It's a to the m times b to the m. Each one gets raised to that exponent. So in here, the 2 is going to get raised to the third, and the r is going to get raised to the third. So it's 8. The volume with 2r inside is 4 over 3 pi. This is now 8r to the third. Or pi. Now, does anything reduce? The denominator, and the only denominator we have is a 3. So looking in the numerator, we have a 4, a pi, an 8, and an r to the third. 3 does not go into or reduce any of those. So there's no common factors. So across the top, 4 times pi times 8 is 32 pi over 3 r to the third power. And that's how you write it, because again, you are plugging in r. I don't know what r is, so I still got an r in the problem. I didn't plug in just a number. I plugged in something with a variable, so I'm going to have a variable in my answer. Now, this is what's cool. Well, to me. The volume, I doubled the radius. That's what this is. If it was 1r, it was 4 pi, or 4/3 pi r to the third. If it was just 1 pi. If I double the radius, the volume is 8 times bigger. It's 8 times bigger.
Or you pi by 40. It's already 32 pi.
4 times 8. 8 over 1, 8 r to the third over 1. Should multiply the numerators. If I tripled it, it would be 27 times bigger. When you have similar objects, a two-dimensional square. Okay. The area to the volume. The area of the volume. If I double the length of the sides on a square, so instead of a 2 by 2, so the area is 4. If I make the sides 4 by 4, this is now 16. You square this. The area is now a square bigger. So the relationship, if you double it, you're squaring it and making it bigger. If this was 3 by 3, this would be 9. If I double it, it's now 6 by 6. This would be 36. Double it, multiply by 4. Okay, it's a square of the proportion. Make it a cube. So if it's a cube, let's go 2 to 2 to 2. The volume is 8. If we double it, 4 to 4 to 4, the volume is 64. I doubled it, so the scale factor is a 2. The scale factor is a 2. So what is the proportion of the volumes? 2 to the third, I have to multiply by 8. If I triple it, 6, that's a 6, that's a 6. 6 times 6, that's 216. Okay, if I triple it. So the scale factor is, if you look at the scale factor, 3 to 2, all right. 6 to 2, scale factor is 6 to 2. So scale factor is 3. So to go from here, 216 divided by 8 is 2, 16, 56, 27. So I tripled it. So that means I multiply by 3 to the third. The cube of the scale factor, because it's 3-dimensional. That's the ratio. Okay. So if the ratio, if the scale factor is A to B, if the scale factor of the lengths of two similar things, if the scale factor is A to B, then the ratio of areas is just going to be A squared to B squared. And the ratio of volumes is going to be A to the third to B to the third. Volume is 3-dimensional. That's why it's a power of 3. Area is flat, 2-dimensional. That's why it's powers of 2. Okay. All right. You have one last quiz question on the closed interval from 57 to 66. So let me pull that up. And today you're going to start your quiz at 2 o'clock. 2 o'clock to do 2 problems. And I'm sorry, but it's over at 2:20. I have to leave. I have to be across town and on the other side in Clovis by 3. And I apologize for that, but that's why I'm going to start at 2. So we've already done 57, 59, 57, 59, 61, 60, 61.
Is this the 1.3?
Yeah. And 62. This is where your second question comes from. $63. 63. Find the domain g of x is equal to 1 over x minus 3 over x plus 2. There are only two things that can hurt your domain. We always want to think first that we hope, cross your fingers, domain is all real numbers, negative infinity to infinity. But that's if you don't have two possible things that might go wrong. The two things you have to be concerned about is there a potential, is there a potentiality of 0 happening in the denominator or taking an even root of a negative number? So you need to be aware, be on the lookout, watch out. Numbers over 0, that hurts domain. And even roots of negatives. Well, that doesn't have any roots in it, so this is not the problem, but it does have fractions. The fractions have x's or a variable in its denominator, so we have a problem. We have a problem. There is a potential that if I plug in something wrong for x, it would make these two denominators possible zeros. Now, you could try every single possible number that exists and then start writing them down, or you can think it through. Just look at it from this perspective. What would cause a 0 in this 1 over x's denominator? What can you not use for x? X cannot be 0. Here's what the whole idea about finding domain. You're trying to find what can we plug in? What are we allowed to use in that function? And you want to write it down. Now, hopefully it's all real numbers. If there's a potential variable in the denominator, then you probably want to approach it from this perspective. In order to figure out what we can use, you first have to go through what can we not use. I can't plug in 0 into this fraction because I get 1 over 0. Can't use it. X better not equal 0, or I get 1 over 0 minus 3 over 0 is okay here. 0 plus 2 is 2. That's fine there. But 0 here, no can use. So in that fraction, no 0. In the other fraction, what is there any restriction? Which one? The whole thing, the x plus 2 better not equal 0. So if the whole thing can't equal 0, then x better not equal -2. That denominator, I can't plug -2 into its denominator because if I plug in -2, -2 plus 2, that makes a 0. Not allowed. So you're like a detective. What is like eliminating all of the things it's not gonna, you know how I don't know if you watch any procedural shows, but they want to fingerprint everybody so they can eliminate the ones who, just want to eliminate you as a suspect. They always tell a husband, we're going to just fingerprint you so we can eliminate you from as a suspect. Yeah.
So I at first thought it was -2, but just some people have questions, but the minus the negative in front of the 3 over x plus 2, would that not affect the denominator?
So here's the deal. You wouldn't do this subtraction until after you simplify this fraction.
Okay.
So if you just plug in -2, that denominator is already 3 over 0. It's already undefined. You have a problem.
Okay.
Yeah. That's a good question. It's not a dumb question at all. Okay, so now those are the two bad guys. The domain is every single real number except those. Again, they don't do a great job of saying write your answer using interval notation, but the quiz does. Interval notation. I really believe if you struggle, look at a picture. Just see it on a number line. It'll help. If I make a number line, And you don't have to on your quiz, but there's 0, and here's -2. Those two numbers are not allowed to be used in the domain. So they would have open circles if you were going to do a graph of a number line. Now, the domain would be every other number except those two numbers. So we would shade everything to the left of -2. We'd shade everything in between -2 and 0. And we would shade everything to the right of 0. Everything except -2 and 0 are allowed to be used. So now I have a visual of what I'm supposed to write as an interval. So from left to right, my interval is going to go from -infinity. And it stops at -2, so comma -2. On infinities, it's always a parenthesis. Now, at -2, that is also a parenthesis because it doesn't equal it. That's an open circle, so that's also a parenthesis. If it does equal the number, that's when you put a bracket, when you do have equals. Then you get to use the numbers in between -2 to 0. So again, from left to right, the next interval goes from -2 parentheses, and it goes all the way to 0. And again, 0 is not allowed, so parentheses. And then the last interval, you get to start with 0, but you don't get to use 0, so that's a parentheses on the 0. And it goes forever to the right, which is infinity. And infinity is always parentheses. Now, one last little thing. It's this interval joined together with this interval, joined together with this interval. The union of those intervals. It's the union of those intervals. That's the domain of that. Now, honest with you, I wouldn't do that to you on like the quiz, just like learning it right now. I might do it to you on a test, but I'm not going to do it this quiz. On a quiz, I might like stick with just one of those fractions. If I was going to give you a fraction. Okay? Remember, I try not to be an asshole. I try, I really do. I'm going to work. I really do try. So I want to make sure that you don't panic. That's why I do the warm-ups as well. So you have something that guides you to take the quiz. Right. That's what we want to do with 1.4 now. Finish up 1.4. Actually, I also put it over here. So if you have any other questions on 1.3, I'll give you some time to ask those. Then we'll continue our 1.4 notes. And then again, we'll start our test, our quiz at 2. And then on Tuesday next week, finish up 1.4 and get it going on 1.5 and 1.6. I know I'm going really slow. I mean, I'm going too slow. I just want to make sure you're aware of that I know that I'm going too slow. And I'm trying to get a read of the room. You know, you probably are tired of me asking for some kind of feedback, but I'm trying to get a read out of you guys. I can only tell about how slow I need to go or how quickly I can go if I get some kind of, you know, interaction out of you sometimes. So I've been going slow because I'm not getting anything going. I guess I'm not getting, I got like, you know, I'm explaining almost every little thing. And some of you are going, really? You're explaining that? But some people need it. Some people, you're over there going, come on. Come on. So it's kind of like if I need, and that's why I want to be in a classroom, because I can get feedback if I'm not looking at a bunch of blacked out screens. It works better this way, in my honest opinion. At least I teach better with people. But if I'm not getting feedback, I'll be up for it again. I always say I'll be on. Back in the old days, before the pandemic, I couldn't get my classes shut up. They were always yapping with each other and they were yelling things out at me. I don't know if it's the mask or what, but I couldn't get people to shut up. Now it's like I can't get people to say boo. So we gotta, I need you to help me help you as best I can. I need to be able to gauge what I need to do. Okay. So we are gonna pick up some speed. Now, I'm hitting a lot of details and I'm kind of holding the hand, but I gotta helping you onto the bus. Now I gotta drive the bus. So are there any other questions from 1-3? 1-4, as you can see, I'm basically laying it out in terms of what ones I'm going to do and which ones I'm just going to talk about. Again, it's a calculator demo because not everybody is familiar with how to enter some of this stuff in. And there's a couple in here I've never done before. I've never entered in a piecewise function into a calculator before. The step function, I've never entered in the step function before. I figured it out, but it's just a matter of until you actually have to do something, that's when you learn how to do it. I prefer to do graphing with pencil and paper, do it by hand. But they're also, hey, we have technology, we're going to learn how to do something. So what we covered, really need yeah. Covered already. Left off, we talk about increasing, decreasing. Talk about that formal definition right there. And that's the important thing is I'm not going to hold you responsible for this formal definition, but this is the language that math is written in your next level. How do you know if a function is increasing? How do you know it's going from left to right? That it's getting bigger. Well, first of all, how do you understand what left to right means? The function is increasing on an interval for any x of 1, x of 2, for any two separate x coordinates in the interval, where the first x is smaller than the second x. That means the first x, x of 1, is on the left, and then x of 2 is on the right, because x of 1 is smaller. So we are going from left to right. X of 1 to x of 2. X of 2 to x of 3, x of 3 to x of 4. It's increasing if the y coordinate at f of x of 1, that's a y, is smaller, is less than, below what f of x of 2 is. So when you plug in x of 1, it's here. And when you plug in to the left, to the right of it, x of 2, it's got to be higher than that. The y is bigger than this one. That means the function increased to get there. That's the definition of increase. If we just say, oh, it gets bigger, that's not math. This is how you describe it mathematically. How is it decreasing? Again, from left to right, from x of 1 going to the right, x of 2. The y value at this first one, x of 1, is bigger than the next one, f of x of 2. Then it's decreasing. It's going from bigger numbers to smaller y values. How do you know it's a constant? Constant means it doesn't change. So when you plug in the first f of x of 1, the y value, and you plug in the second one, f of x of 2, they're the same thing, they're equal. They didn't change as you went from one to the other. Okay? Again, as you go from left to right, it's always from left to right. Now, on a picture from left to right, as you go from left to right, this interval from -2 to 0, on this interval, this function is decreasing. Then from 0 to 2, the interval is constant. And on this interval from 2 to 4, the interval is increasing. Now, we're not going to worry too much about are they open or closed intervals. But typically, they are, when we talk about increasing and decreasing intervals, they are typically, unless you are specifically told, they are typically open intervals. On what open intervals is the function increasing or decreasing? And then if you have to deal with closed intervals, they will tell you on what closed intervals is something increasing. Where it becomes confusing is we don't tend to see graphs that look like this. They will have arrows like that because they go forever to the left and forever to the right. So when somebody sees that arrow going up, over here, they think that's increasing because that arrow is pointing up. But we're not looking at the graph as it goes to the left. We're looking at it, we're sliding down this way. We're always going from left to right on the curve. So going from here to here, it's getting smaller. Okay. And then you have the definition of relative extrema, or relative maximums and minimums. I know it's loud. So relative max and mins. I actually had a student in class when her name was Min. So we said, let's find the min. There she is. Okay. A relative. That means kind of like in your own little neighborhood. Compared to everybody around you, you're the best. You're the maximum. Okay? But relative to the people around you, relatively speaking. You know, relatively speaking, in your own neighborhood, in your own family, whatever, your local arrangement of points, what's the smallest value? That's your relative minimum. The next level would be what's the absolute maximum, what's the absolute minimum? In other words, for the graph, what is the exact highest maximum, what's the highest point? What's the absolute minimum? What's the absolute smallest value? But relative is this. This is a picture of a relative, and they say minimum, relative min, because in this neighborhood, the function goes down and then it goes up. That is the lowest point out of all the y coordinates in this local area. Then as you go up and reach its highest point here, that's a relative maxima, because as soon as you reach that point, then the rest of those points in the neighborhood are all smaller than that point. So relatively speaking, in this group of points, that's the highest value. So that's the relative max for that set of points. And then as you go through here, you reach a bottom point again. Relatively speaking, that is the smallest value of y in this set of points. But if you look at these 2 points, the one on the right, sorry, the one on the left, my right, the one on the left is lower than this one. So that one is smaller than this one, but in their neighborhoods, they're both, that's a relative minima or min for its group of points, and that's a relative min over here in its set of points. It's just the bottoms of curves. And then the function, we call this increasing. It increases as you go from here to here, and then it decreases again. But at that point, it's the highest point we reach in that set of points. So that's a relative max. And you look at these 2 maxes, that's bigger than that one is. So that one should be, well, why is it relative? Well, because this one is still relative. And who knows what the graph does past this? Maybe it goes up even higher afterwards. we're not told what the absolute, we're not asked to find what the absolute maximum min is. We would have to have more information. By definition, a function value f of a. If it's f, that's the y value. So f of a is the y value when you plug a into the function. Now, f of 3 is the y value when you plug in 3. F of a, the y value when you plug in whatever a is. F of a is a relative minimum. These two things. Of f, when there exists an interval, you gotta have an interval from left to right, x sub 1, x sub 2, that contains a. So a is somewhere in between x sub 1 and x sub 2. And as you go from here to there, there's a whole bunch of x's. X sub 1, x sub 2. You have an infinite number of values. A is also in there, but there's a whole bunch of other ones. For all those other x's, f of a is the minimum if the value of f of a is less than or equal to all those other y values. If the y value is the smallest at a, then all the other values, that's your minimum. And that's how it's written mathematically. You flip it around, if f of a is greater than all the other f of x's in that interval, it's a relative max. Okay, that's the language that is, you know, if you go past this class, and right now I'm probably going, I'm not going past this class anymore. When you go past this class, that's the language you're going to have to evolve into speak. Okay, you're going to change your way of thinking. It's not just about plugging in numbers. It's about understanding. It'll make things easier for you. Okay. In calculus, we figure out the maximum min by hand. Here, you're going to use your calculator. And then the last thing before we start doing problems is the step function. Okay. So the greatest integer function. Greatest integer. The greatest integer. So this is the, you know what to do if you see absolute value of x. That's the notation. That means whatever comes out of that absolute value as a number, you take the positive. It's the distance from 0. You know what you're supposed to do if you see 2 to the x power. Whatever x is, you're going to raise 2 to that power. You know the notation. Hopefully you know what to do when you see this notation. Natural log of the number. You know you're supposed to take basically base e of that number. What e to what power is that number? These are all brand new notations that have been introduced probably up until like your last math class, if it was algebra 2. So here's a new one. F of x is equal to the greatest integer function, otherwise known as the step function. And it looks like that. Like 2 brackets around an x. And you got to hear the definition to know what to do. Otherwise, when I see that, I don't even know what it is. Domain, all real numbers, negative infinity to infinity. You can plug in anything, plug in integers, plug in fractions, you can plug in decimals, you can plug in pi if you want, plug in anything you want. Range. The only thing that comes out of the step function is integers. In case you're wondering, integers. Negative numbers, positive numbers, and 0, no fractions, no decimals, no pies, no square roots. It's the positive and negative whole numbers. 0, 1, 2, 3, forever. Negative 1, negative 2, negative 3. Nothing in between, just those are the integers. Okay. X-intercepts in the interval, y-intercept. We'll talk about that when we do our graph. the answer to the step function, it's a constant between each pair of consecutive integers. And we'll talk about that when we actually work it out. And it jumps vertically 1 unit at each integer value. And this is the parent function. This is what the basic bare bones step of X looks like. The greatest integer function is the greatest integer less than or equal to X. So whatever I plug in, what comes out, this little symbol right here, is going to be the greatest integer that is less than or equal to X. The greatest integer that is less than or equal to whatever I plug in. So, anytime we need to figure out something and graph something brand new, what we prefer to do is take tape. So here is the table. We're going to plug in X, and we want to know what f of X is, which is our step function, greatest integer less than or equal to X. And typically, whenever we want to make a table like this, we tend to start with nice numbers, and we're just going to leave a little room for trying to write down what I'm writing down. But I'm just going to start with 0. And then when I go to 1, and then I probably go to 2, and then maybe plug in 3, and let's see what happens. But when I plug these things in, again, I don't have like a square. I don't have, 2x plus 4. I don't know what I'm going to do with it except say what I'm about to say out loud. So when I plug in 0, f of 0 goes in here like this. And what I want out is the greatest integer that is less than or equal to the 0 I just plugged in. The greatest integer that is less than or equal to 0. What is it? 0. So the integers you have to choose from, remember, integers, -3, -2, -1, 0, these are integers. 1, 2, 3, 4. Those are integers. So the biggest integer that's less than or equal to the 0. 0. The 0 goes out. Ordered pair, x is 0, the y is 0. So I would have a point right here. Okay. Then I plug in 1. F of 1 would be the step of 1. So as we say it, we're going to look the greatest integer that is less than or equal to a 1. So the biggest integer that's less than or equal to the 1. So what is it? 1. The biggest integer that's less than, so 0, that's not very big. 1, 2 is not less than the 1 I just plugged in. The biggest integer that's less than or equal to the 1 is a 1. This equals 1. So when 1 goes in, 1 comes out. So the next point is here. 2, F2. So the greatest integer that's less than, so less than a 2, but or equal to the 2, which is going to be the what? Do we see a pattern yet? Okay, so 2 goes in, 2 will come out. And greatest integer that's less than or equal to a 3 would be a 3. And if we're not careful, we might do something crazy or silly and think it just goes straight line like that because we just connect the dots. This is not one of those kind of functions. So let's try something else. Let's try 0.5. So, plug in a half. So f of 0.5, f of 1/2. And just looking at it, go, I don't know what that is. But say the greatest integer that's less than 0.5 or equal to 0.5. Well, there's no integers that are equal to 0.5. So what's the greatest integer that's less than 0.5? 0.5 would be right about here. 0. The greatest integer that's less than 0.5 is 0. So when I plug in 0.5, that comes out. If I plug in 0.75, that was 0.75. The greatest integer that's less than or equal to 0.75 is going to be 0. Because if I plug in 0.75, the greatest integer that's less than or equal to it, well, 1 is bigger than it, so it's not 1. There's not, 0.75 is not an integer, so it's not 0.75. So I have to go with less than 0.75. So the greatest integer that's less than the 0.75 is 0. So we get 0 again. So it's right about here. This goes on forever. You can keep on going forever and ever, get infinitely close to 1. The greatest integer that's less than or equal, so how about 0.9999999? Well, the biggest integer that's greater than or less than 0.9999999 is 0. So you get really, really close to that 1. But as soon as you plug in 1, what happened? What came out? 1. It jumped. As soon as we plugged in 1, it's up here. So when you graph this, it looks like this. All of these answers in between 0 to 1, the answer is 0 until you get to 1. And so there's an open circle on that little horizontal line. And then when you get to 1, it jumps up. Because that's where the next set of answers are going to begin. And when you plug in the next set of numbers between 1 and 2, 1.23, the greatest integer that's less than or equal to 1.23. Well, 2 is bigger, so that will work. Less than, no, there's no integer equal to 1.23. So the biggest integer that's less than that is a 1. So the y value would be here 1. Everything in between 1 to 2, every fraction, every decimal between 1 and 2, all of the y's are going to equal 1s. 1.999, the biggest integer less than or equal to that, is 1. When we got to 2, the greatest integer less than or equal to 2, we're up here at 2. It jumped up. So that means you have an empty circle right there. And then for every number between 2 and 3, all these decimals between 2 and 3, the greatest integer that's less than or equal to everything between 2 and 3 is going to be a 2. They're all right here. When you get to 3, it jumped up. So there's an open circle right there. Everything between 3 and 4, the greatest integer is going to be a 3. And then when you get to 4, the greatest integer less than or equal to a 4 is going to be a 4. So it jumps up. Open circle, jumps up, open circle, jumps up, open circle. That's why it's called a step function, because it looks like steps. When you're over here on the negative side, negative 1/2, negative 0.5. The greatest integer that's less than or equal to negative 0.5. So less than, so it can't be 0. 0 is bigger than that. 0.5 is not an integer, so it's not equal. So less than would be negative 1. So in between negative 1 and 0, they're all right here. The greatest integer less than or equal to negative 1 is negative 1. And then when you get to 0, an open circle, it jumps up. So you have steps in all directions. And that's what our step function looks like. One step at a time. Now we're going to sketch the piecewise functions as an example. The last little piece, I'm sorry, I thought the step was, but the last piece is the odds and evens. The definition of odd and even functions is about, technically, it's about symmetry. Okay. Symmetry about the x-axis and the y-axis. If it's both, then it's symmetry about the origin. Lots of graphs have symmetry. It just depends upon where that symmetry or the line of symmetry is going to be. If your graph has symmetry about the y-axis, left and right, if it has symmetry, if you could fold a piece of paper on the y-axis and every point over here on the right folds over here and matches up with a point over here on the left, that's symmetry about the y-axis. If it has symmetry about the y-axis, it is an even function. It's even. Look at how it's defined. Yeah, symmetry about the y-axis, but that's if you have a graph. What if you don't have a graph and you don't want to graph it? It's about the ordered pairs. These 2 points would have to match up perfectly. This point over here is x units to the right of 0. And the y value is a y. That's why the ordered pair right here is xy. If it is going to have symmetry, then when you fold it over, it should be x units in this direction. And if you're going to the left, then the x coordinate over here is going to be negative x. But the y shouldn't change. The y value should be exactly the same y as it is on the right-hand side. So the definition for even, if f of negative x is equal to just plain old f of x, the original function, y value. If I plug in the negative value of the x, or the opposite of the x coordinate, and I still get the same y coordinate, the y coordinate doesn't change, then the function is even. X squared is even. Not because it's x squared, that would be too simple, but because of the symmetry. When you graph x squared, it looks like a parabola, it's like that. But look, if I go f of positive 3, I get 3 squared, I get 9. If I plug in the opposite, if I plug in negative 3, I get negative 3 squared, I still get positive 9. If I plug in the opposite x coordinate, I get the same y coordinate. On this one, it's positive 3, positive 9. On this one, it's negative 3, positive 9. That's how you know it's even. If you change the sign of the x's, but the y's remain the same, even. The y's remain the same. To show you that not every x squared is even, I gave you f of x was x plus 2 squared. That's not going to be even, and I'll show you why. If I plug in f of, just go 0. Well, no, 0 doesn't have a sign. Can't be. Let's plug in, pick a number greater than 0. Give me just an integer, greater than 0. What? 1? Okay. F of 1. Plug in 1, I get 1 plus 2, and then I square it. I get 3 squared, I get a 9. So when 1 goes in, we get 9. If it's even, then when I plug in negative 1, the opposite, I better still get 9. So negative 1 plus 2 squared is equal to positive 1 squared, and it equals 1. So when negative 1 goes in, the opposite, I don't get 9, I get 1. It's not even. Even though it's a square, that has nothing to do with odds or evens. So it's negative x, do we get the same y value? Okay. Odd functions. This is an example of an odd function. This to me, that looks like a cube root of x, x to the 1/3 power. But again, that's a nice coincidence. 1/3, yeah, because of 3. Well, it's not a 3 to 1/3. 1/3 is not power even. It's about symmetry. If it's odd, it has symmetry about the origin. The symmetry is about the origin. And to get symmetry about the origin, you have to flip it across the y-axis and then flip it across the x-axis. It takes 2 flips to get symmetry about the origin. So that means you're over here at positive x, and when you flip it over here, you're now at negative x. And then to get it down here, you have to take this positive y value, and when you flip it down here, you're now at negative y. So here's the thing. If a function is odd, then if x, y is on the graph, the opposites have to also be on the graph. The exact opposites have to be on the graph. So if you have 3, 2 on the graph, then negative 3, negative 2 better also be on the graph if it's odd. Both have to be different signs. That's what makes something odd. The x's and the y's opposite signs are both on the graph. So it's odd. If we plug in negative x, I plug in, here's my 3, 2. I plug in negative 3, and on this side, I get the opposite y value. I get the opposite of that y value, negative 2. So when I plug in the opposite of x, I get the opposite of the y value. I get f of x with a negative of it. The y is now an opposite sign. That's how you determine if it's an odd function. Okay, signs have to be different. And then this right here, this is just symmetry about the x-axis. This is a reflection across the x-axis. Up here, you have a positive y. Down here, you have a negative y. The x's are the same. That's neither odd nor even because it's not even a function. How come that's not a function? Vertical line test. The graph intersects the vertical line intersects the graph in more than one place. And not to mention, for this one x, you have two different y's that come out. So if your graph looks like that, it's neither odd nor even because it's not even a function. It's not a function with respect to the x. Okay. You understand in chapter 1, a lot of these concepts are spread out over an entire semester. And they're just, jammed into this one chapter. Let's look at so pick one out of the first 6. 1, 2, 3, 4, 5, or 6. I'll do 2 of them. You tell me what you want to see. Number 6. Given f of x is the greatest integer function of x, in what interval does f of x equal 5? So that means the y value is a 5. So where does the x come from? So if we had our picture back up, 1, 2, 3, 4, 5. So somewhere over here, it's solid on the left-hand side to an open circle on the right-hand side. And this is where all of the function is equal to a 5. The function equals 5. What they want to know is, what is the intervals for x? What answers of x are going to go in to make that happen? So let's work backwards. 5 is the greatest integer that's less than or equal to what numbers? So, obviously it's not between 0 and 1, 0, 1, 2, 2 and 3, 3 and 4. Okay, I'm off center here. One, 2, 3, 4. Here's 5, and here's probably 6. So if it's between 4 and 5, the greatest integer that's less than or equal to a 4.5 goes back down to a 4. So something greatest integer between a 5 and a 6, a 5.5, the greatest integer that's less than or equal to a 5.5 drops back down to a 5. And when you get to 6, it's now up here. So it's in between here and here, 5 and 6. You see the closed circle right here? That means when you plug in 5, we get 5. So it's a closed interval. I said 5. It's a closed interval on the 5. But when you get to the 6, when I plug in 6, I don't get 5. So it goes all the way up to the 6, but not including the 6. So it's a parentheses. So a bracket on the 5 all the way up to 6. Parentheses. That's one of them. Which else? Oops. Pick one more. Thomas chicken. The graph of a function f is a segment. Is a segment from the ordered pair 1.1, 2. And again, if you make a picture, it helps. So from this point, 1, 2, to the point 4, 5. So 2, 3, 4, 3, 4, 5. So 4, 5. And it says it's a segment. So that means not a line. Segments have endpoints. Okay.
Oh, I see. So the domain would be negative infinity. And then, no, am I wrong?
So they want the domain of just the segment. Infinity is not involved at all.
Oh, they just want it in between.
So bracket 1 to the 4 is the only thing on the x-axis that makes that segment.
Okay.
That's it. Okay. 7 through 10, you pick one odd and one even. So 7 through 10, okay, use the graph of the function to find the domain and the range, and then find f of 0. So you're not even graphing it. You're looking at the picture, and just by looking at the picture, domain, range, and then what is f of 0? So 7 or 9, which one?
7.
Number 7. So the domain is the x's. Now, they don't put closed points right here. Here they do. So it doesn't go any further to the left, it doesn't go any further to the right. Here, when you don't have closed points, you can't assume that it just stops here even with -2. In fact, it doesn't even look like it. So you have to basically think that that goes down forever. And it's got a little bit of an angle going to the left. So it's hitting every single x to a negative infinity and every single x going to positive infinity. So the domain is all real numbers, negative infinity to infinity for the domain. The range. Now, that's 3, that's 2. It's kind of hard to not see that this would be 1. Because that one you kind of have to assume because there's no other, it has to, if you're going to do the domain, you have to make, or range, you have to put a 1. This is what I talked about on Tuesday. Sometimes it's better before you start writing down the range, going right to the answer, use inequalities, less than, greater than. And I kind of walk myself through it and I say, all right, the graph is pointing down here, and I know it's going down there forever. Are there any, the range is the y values. Are there any y values up here at all? No. The highest y value is here at 1. The rest of the y's are below the 1. That means below means less than. And because it touches the 1, it's less than or equal to the 1. In that picture, all of the y's are less than or equal to the 1. If this helps, a number line. On a number line, that would be a closed circle, closed dot on the 1. Less than would go to the left. So the domain, or sorry, I'm using the wrong word. The range would be negative infinity. And it would stop when you got to 1, and it would be a bracket on the 1 because it actually equals the 1 at its highest point. So that would be the range. From negative infinity down there on the y-axis, and it goes high as it can go is up to that 1. And that's the range. Okay, now you can pick either 8 or 10. Number 8. Again, assuming that those are going on forever because it really can't tell when it stops. There's no endpoint. It says it stops, starts and stops. if it gave you explicit, hey, right there is 2, 5, and they put a big old point there, then the domain stops at 2. But it doesn't, so it's going forever left on the x-axis, it's going forever to the right on the y-axis. Domain is all real numbers, negative infinity to infinity. And then here's another part of the good news. One arrow going down forever, the other one's going up forever, and there is no break here at all. Every single y coordinate on the y-axis has a chance to be an answer. So the range is also all real numbers. It's going from negative infinity to infinity on the y-axis. That takes care of 7 and 8. Number 13, calculated MR. Use a graph utility to graph the function and estimate the domain and the range. So square root of x plus 2. So y equals the square root of x plus 2. And so we want to estimate the domain range. Now, I'm not changing my window. I have no idea what my window is set. I'm just going to go ahead and hit graph. Okay. Zoom instead. So luckily, my window was in a, for whatever I graphed the last time, it was in a window that allowed me to get at least some of the picture. But domain. Do you see any part of the graph over here at all? No. There's no graphing going on over here. The graphing doesn't start until we get to this x coordinate. And because now I can use my calculator, if I look at the window, I actually pay attention to look at the window. It says the x min is -5, and the x max is +3, and the x scale is counting by 1s. And it goes up from -0.5 to 7. So this is -5, -4, -3, -2, -1, 0, 1, 2, 3. This is +1, 2, 3, 4, and all the way up. So it looks like all of my x's have to be greater than, because I can't use anything to the left of -2, greater than or equal to -2. Okay. That would be my domain. Using interval notation, because there's an equal, it would be a bracket on the -2, and I could plug everything into infinity. That would be my domain. And then the range is your y values, and it doesn't look like there's any graph down here. And to be sure, I can change the window for the y's and just increase the window down there below and make that -2 to give a better picture. Yep, there's nothing going on. And that makes total sense because the square root of x plus 2, there's no way whatever comes out of the square root would be a negative y value anyway. Square root of a thing is going to be a positive number no matter what. Unless there was a negative in front, which it doesn't have. So they would all be positive numbers. So it's going to go above 0. All of my y's have to be greater than 0. And then when you're right here at -2, it's equal to 0. Because if you plug in -2, -2 plus 2, 0, square root of 0, the y is 0. So right here, -2, 0 is actually a part of the graph. So since this is your range in inequalities, using interval notation, they go from 0 to infinity. That's the range. All right, 17, A, B, C, D, E, F, G, H, I. Now, I'm doing 17 because I don't want you to sit there and freak out because you got to do parts A through I. A, domain and range. B, determine, sorry, A is what's the domain, B is the range. C, find the values for X, which f of X equals 0. In other words, find the X-intercepts. So let's do those first three things. So domain and range on this picture. Again, assume in the picture and it goes left and right forever. So the domain, the x's, you're using everything to the left and everything to the right. So the domain would be negative infinity to infinity. And then the range is your y's. Are we having any y's down here below -2? No. So that means all of my y's in the picture, they have to be above negative. That means greater than -2. And at this point right here, it does equal to -2. All of my y's have to be greater than or equal to the -2. So that means the y values go from -2 to infinity. And because you have equals, it's going to be a bracket on the -2. And it goes to infinity. That's the domain rate. And then it wants when does the function, when does f of x equal 0? So that means, remember, this is the y value. When does y equal 0? Y equals 0 when it crosses the x-axis. They want you to find the x's. So what's that x equal? So that x equals to -1, and what's that x equal? 3. And those are your two x-intercepts. So far, okay? And then B. What are the values of x from part C referred to? Oh, X-intercepts. Okay, what do they mean? That's what they're called, X-intercepts. And then E, find f of 0. F of 0, so when x is 0, f of 0 plugs 0 into the function, so you're trying to figure out what the y is. X is 0 on the y-axis. So when x is 0, you're finding the y-intercept. When x is 0, that y right there is -1. So f of 0 is -1. It's just the y-intercept. And then what is the value from part E referred to? Y-intercept. Part F. And then G. What is the value of f at x equals 1? So if we translate that, what is the value of f at x equals 1? They want to know value of f. What does f of 1 equal? Well, when x equals 1, the y value was a -2. So So f of 1 would be -2. Okay. And h, what is the value of f when x is -1? F of -1, that y value right there is a 0. Oh, and also, what are the coordinates of the point? You want that from G and H. The coordinates, -1, 0, and over there, 1. And then last but not least, I. The coordinates of the point on the graph of f at which x equals -3 can be labeled -3, f of -3. Or -3. Now, -3 is over here. There's -2. There's -3. Can we predict? Well, if we plug in 0, and that's -1. We plug in -1, we get 0. We plug in -2, it looks like we're getting 1. So when I plug in -3, we should be getting 2. Because it's on a straight line. It's got to maintain that same incline. Every time I go up 1 this way, I go left that way. Up 1 left, up 1 left. So if I go left, I got to go up 1. So you're just using the slope. Or you can also plug it in here. F of -3 is the absolute value of -3 minus 1 and then -2. That's the absolute value of -4 minus 2. So that's +4 minus 2, and we get 2. Okay, that takes us. So whatever you're going to use while you take your quiz, pencil is always preferred. And then when you're done, you're free to go, just turn it in. Please make sure you write both your first and last name on the quiz. Again, 3 problems for part A, number 1. Plug in the first number, plug in the second number, plug in the third thing, last expression. And then number 2, write the domain using interval notation for that function. Oh. All right, Charles, that's it for today. I'll see you next week. You get better, all right? All right.